Please welcome Lucy Cramp. Lucy undertook a BA in Archaeology and Anthropology and then an MSc in Archaeological Science at the University of Oxford, followed by a PhD at the University of Reading. She is now Associate Professor at the University of Bristol, specialising in lipid residue analysis and co-directs the External Service of Organic Residue Analysis at the University of Bristol. Okay, thank you, Lucy. Take it away.
Right, thank you very much, and thanks very much for inviting me to talk today. So it's really nice to be here, and what I want to do, if that's okay, is just spend a bit of time just overviewing the approach, organic residue analysis, particularly applied to pottery, and then sort of followed on with a few examples of the types and the different scales of research questions that we can tackle using this approach. So the approach, organic residue analysis, and I'm focusing today in particular on lipid molecules in pottery. That's the most widespread molecule we tend to focus on. It tends to survive very well over archaeological timescales, fats and oils, that not very soluble in water. So they're a good class of molecule to try and look at. And the approach itself is based on the extraction and characterization of preserved lipid fingerprints. And so, as I'll talk about in a minute, this is particularly applied to archaeological ceramics because they're great. They're great for this. But the principles of the approach can be applied equally to other kinds of archaeological materials as well that these kinds of amorphous residues might be associated with. So it'll be exactly the same approach, but it can be applied also to carbonized residues that are adhering to pottery or other kinds of artifacts. It can be applied to other kinds of balms or creams, mummy balms, bog butters, even anthropogenic lipids extracted from soils and sediments as well. So it's all exactly the same kind of approach. In terms of what we're doing, we're extracting out these lipid signatures from pottery or wherever they're coming from, and looking at this fingerprint of different compounds that's being extracted. And this can help us to identify the one or multiple kinds of sources that these residues are resulting from. How specific it's possible to be about the origins of these residues depends on two key things. The first of these is how specific this distribution of different biomarkers is in the original commodity in the first place. So for some kinds of products, different kinds of plant oils, for example, it might be that the lipid signatures of all of these might be quite similar across lots of different kinds of species, genera, families, and so on. Or there could be cases where there are really quite specific biomarkers. So this will kind of determine the potential that you've got as to how specific you can be of different kinds of commodities. But the other thing that's really important is, of course, we're looking at lipids which are at least hundreds, if not often many thousands of years old. And so these signatures will have degraded over time. So what also needs to happen is that as these lipids degrade, if there are distinctive signatures in the first place in the fresh commodities, this needs to survive in some kind of recognizable state over archaeological timescales. Otherwise, you start to lose some of this diagnostic information, and I'll talk a bit more about that in a moment. So, as I mentioned, probably the lion's share of organic residue analysis is conducted on residues absorbed into the fabric of pottery. And this is for probably a couple of main reasons, one of which is that pottery, the fabric of pottery, is brilliant for this. So lipids absorb into the fabric of the pot, and once they're in there, they're relatively well protected from both physical and microbial decay. So they're well protected in there, and they can be extracted out again afterwards. And the other good thing about pottery is that once pottery is introduced or appears in a region, it tends to be quite abundant at archaeological sites. It survives quite well. And this means that we have the numbers to start sort of building up projects to compare diet or pottery use over time and space. So when we're talking about pottery, generally what happens is people will design a research project, and I'll talk a little bit more about that later on, and we've got lots of guidance on how to do this. Generally, we're looking at multiple sherds because you might, from Britain, for example, residues might survive in, it's pretty good from Britain, but maybe 50–80% of pot sherds might contain a residue. So you want to have quite a few sherds you're analysing just to recover enough lipids to actually start building up patterns or interpretations. But you also want to have enough pot sherds that you can start to sort of meaningfully interpret these patterns. So if you've got a research question that's looking at particular vessel form or vessel shape, If you want to argue that that vessel form is used for something quite specialised, you also want to be analysing some of the non-specialised vessel form as well as a comparison, so you can start to compare the patterns. So the lipids, as I mentioned, we're talking specifically about lipids absorbed into the fabric of the pot, so they're not visible. You can't see them, but they're there. They're very widely there. So we usually take pieces of pottery, the bigger the better, really, but normally it's nice to have a sort of piece about this size. We don't need to sample that much, but it makes it much easier to clean and prepare the pottery because you've got something you can hold that's not the sample you're actually taking. And then we use a modelling drill to to clean away the outer portion, or a sort of a small portion of that pot sherd. So we need to sample about 2 grams. It's about the size of a pound coin. So we clean away the outer surfaces of just a little corner to get rid of any sort of external surfaces that have been in contact with hands or with soil and so on. And then use a chisel to chip away that corner. That's then crushed up to a powder using a mortar and pestle, so it's pretty low tech. And then that powder is then solvent extracted. And once the solvent is evaporated away, you recover this total lipid extract that's been extracted out of the fabric of the pot. So that total lipid extract will have a whole mixture of lipid compounds that have absorbed into the fabric of the pot over its lifetime. So this mixture is then separated out using a technique called gas chromatography, which essentially separates out the different, as you can see here, these are the peaks. It separates out the different compounds present within a mixture, and you can quantify those as well. But then to get the structural identity of each of these peaks, we then combine GC with mass spectrometry, which gives you those, helps you interpret those peak identities too, and that's what gives you your lipid fingerprint, your lipid biomarkers to make further interpretation. So I've got a few examples here of some sort of typical profiles of different kinds of commodities that we encounter from archaeological pot residues, just so you can get a bit of a feel for the different kinds of fingerprints that we see. So at the top, we've got a degraded animal fat. So you can see here, this is characterized by very diagnostic distributions of triacylglycerols or triglycerides. So these, in a fresh fat, these are the main sort of lipid component of the fresh fat. They're made up of fatty acids that you can see here, which are esterified to a glycerol backbone. So this is the whole molecule. So if this was a fresh fat, these peaks would be really, really high and there wouldn't be much else. But of course, over time, these degrade. So you end up with a profile of a degraded fat that usually has these distributions of diacylglycerols, where one of these fatty acids has been lost, monoacylglycerols, and then often what can be most abundant are these free fatty acids here. If we compare this to degraded plant leaf wax, instead we've got this distribution of wax esters here, and then other compounds like alkanes, ketones, alcohols. And then at the bottom we've got a beeswax, which is actually, looks like it's mixed with an animal fat as well, but it's got a composition of diesters and monoesters and degradation products here as well. So as you can imagine, pottery may well not just be used for one thing, either for each cooking event or over its lifetime. And so what we do see, and you can see in this beeswax animal fat mix at the bottom, is if a pot has been used for multiple commodities, then you tend to get a sort of a fingerprint or sort of overprinting of different signatures of different origins within that residue that's been extracted. And what's not possible to determine is whether that arose from different things being cooked together at the same time, as a sort of vegetable meaty stew, or whether that's from lipids accumulating from different sequential events, so being used for stew on a Thursday and cabbage on a Saturday. And as I mentioned earlier, one of the sort of key considerations about how specific we can be is this issue of degradation, that although original compositions of fatty acids can be quite distinctive in fresh fats, as these start to degrade, we can start to lose some of that diagnostic information. So just to give you a nice example here, I've got fatty acid compositions of a fresh milk fat and a fresh fish fat. So these are fatty acids. The number after the C is the number of carbons in the length, so you get different lengths of fatty acids, different chain lengths. And the number after the colon is the number of double bonds. So in a milk fat, you can see it's got high abundances of the C16 and C18 fatty acid, and also relatively high amount of the C18-1, so one double bond in that fatty acid. These are also present in the fish fat, but what's really distinctive about the fish fat is that there's also long chain, so 20 and 22 carbon atoms in the chain, really highly unsaturated fatty acids with 5 or 6 double bonds in them. So if you were to look at the lipid composition of milk fat and fish fat, really, really clearly nicely distinctive. But the issue is that fish fat, or at least these highly unsaturated fatty acids, degrade really quickly. They're very reactive, and there's no chance of them surviving over archaeological timescales. So if we look at a degraded examples of milk fat and fish fat, you can see that we've lost all of the highly unsaturated fatty acids. We've lost most of even the monounsaturated fatty acids. And what we're left with are the saturated fatty acids with profiles that actually now look very similar between a milk fat and a fish fat. So we lose quite a lot of that original diagnostic information. But what we do with animal fats is, if you look at the stable isotope composition of the individual fatty acids, this can help you start to separate out animals from different, basically from different metabolic groups by comparing them with reference fats. So, oops, wrong way. So if we measure the stable isotope composition of the C16 fatty acid and plot it against the isotope value of the C18 fatty acid, for a milk fat, oops, you'd expect it to plot down here, and it usually does. For a fish fat, it would, or a marine fish, it would plot somewhere up here. And of course, if you've got mixtures of fats, if you're using a pot that's being used to cook, I don't know, pig fats and beef fat, you'll get an integrated signature that will plot somewhere on a mixing line between these endpoints. So thinking about the kinds of questions we can ask, one of them is starting to test hypotheses about the function of different forms of vessels based upon their shape and their fabric. I'm just going to whistle through a few examples here because there's not really time to go into any in detail. But one example is some work I did on Roman mortaria back in my PhD to look to see if these were a sort of specialized type of vessel that was being used in a particular different way to other kinds of pots that were being used in the Roman period. And to very briefly give the outcome, what it found was a very, very strong association between mortaria residues and leafy or epicuticular waxes from plants, so some kinds of plant waxes. It found very, very widely in mortaria. In Roman cooking pots from the same sites, we see leafy plants being appearing as well alongside meats, but at much sort of lower levels and much less frequently. So there's a very clear difference in the patterns of the mortaria and their use compared with the cooking pots. And another really nice example from the Neolithic period from LBK Poland is some work by Melanie Roffey-Salk, which was looking at these perforated ceramic so-called sieves, and also other different kinds of forms from the same site, so bowls, these cooking pots and collared jars as well. And this showed really clear patterns between the use of these different vessel forms. The milk sieves were strongly associated with dairy fat, so pretty much all of them had milk residues from them, as well as the bowls as well, suggesting that they might have been used perhaps together for perhaps the bowls being used to collect or contain liquid milk. The cooking pots were associated with meat from animal products, so beef, cattle, sheep, or goat. And the collared jars were quite interesting because they had beeswax residues in them, which where it's possible that came from processing of honey, but perhaps more likely it was beeswax being used as a waterproof coating on the vessel to make it less permeable for containing liquids. And the other kinds of questions we can start to target are looking at either chronological or spatial patterns in dietary practices over time and space. And this can be within a site, it can be between sites, different locations, and so on. So a couple of examples I give here would be some really nice work that was done by Julie Dunn in collaboration with Oxford Archaeology. And this was looking at pottery associated with the medieval Jewish quarter at St Aldate's in Oxford. And so an assemblage of pottery was analysed from that location, but then also compared with pottery from the same location but earlier, so preceding the medieval Jewry, and then also from a contemporaneous site from Oxford, but outside of the Jewish quarter. And again, what this showed really clearly is quite distinct differences with an almost complete absence of non-ruminants, so porcine or poultry fats, coming from residues associated with medieval Jewry. But as we see quite typically in the medieval period, these were present in quite high abundance, both in the earlier pottery from the late Saxon layers, but also from contemporaneous medieval contexts from elsewhere in Oxford. Another example has been looking at pottery from the same phase at the Roman fort at Vindolanda. So this is from a really discrete chronological phase of about 20 years between AD 105 and about 120. And we looked at pottery from inside the fort, from the Scola, the Praetorium, and the barracks, and compared it with pottery which was excavated from the same time period, same phase, from the civilian vicus outside of the fort. And we found some quite interesting differences there, one of which is a higher prevalence of dairy fats coming from outside the fort, and also much higher prevalence of pine resin biomarkers coming from the pottery within the fort. And this, I think, may well be something that's not to do with diet per se, but might be more reflecting perhaps practices of food supply or storage, that these pine biomarkers might have been coming from transport in pine barrels, for example, or possibly an amphora that had a pine resin coating on the inside of them. And finally, we can do some quite large-scale projects, and often this can be through integrating data from multiple projects over time. So between quite a number of us, we've looked at a lot of pottery now from Neolithic Britain, from carinated bowl, from the early Neolithic through to the later Neolithic. And this is kind of an amalgamation of research done by Mark Copley, by Jess Smith, Anna Mukherjee, myself, most recently Isabel Wiltshire, who's also been combining it with dating of lipids as well. And through looking at, we now sort of must have quite a few hundred potsherds we've analysed from the Neolithic period, we can start to dig in a bit more into the use and the role of pottery as it first appeared, and how this role might have changed over time. So what we find very distinctively is that from the early Neolithic period in Britain, we've got a really strong association of pottery and dairy products. So from the early Neolithic period overall, we have, well, at the very least 3/4, if not sort of 80% plus, of pottery assemblages containing predominantly dairy fats. Whether this represents populations who are eating a lot of dairy products, or whether perhaps more likely this is because carinated bowl was being used for quite a specialist role, had quite a specialist purpose, is something that, you know, it becomes harder to answer. I think possibly the latter is more likely. But by the middle Neolithic, what we...
Just 2 minutes.
Yeah. Okay. What we start to see is a shift during the Middle Neolithic, particularly in southern Britain, towards a high predominance of ruminant fats, and then by the late Neolithic, especially in mainland of Britain, again we see an increasing shift towards meat products being cooked in pots. I would just highlight Isabel Wiltshire's work because this has started to give us much finer grained resolution on pottery use within the early Neolithic itself. So by combining this with the dating of lipids and other radiocarbon dates that are available, she's been able to show that the earliest sort of carinated bowl from Britain, from both northern and southern, very dairy. As we get to the slightly later early Neolithic, we start to see this shift away in southern Britain to already we're starting to see some diversification in the use of pottery during the sort of late 39th century BC. So the last thing I will highlight in my last 30 seconds is the dating of pottery lipids. So this means that we can date the individual fatty acids which are extracted from pottery, and we can get radiocarbon dates on each of these fatty acids. So by statistically comparing the fatty acid radiocarbon dates, you get this internal check of the dates. And if they're in statistical agreement, you can then combine these dates to get a combined age for that milk residue or that meat residue that's been extracted from a pot. And what's really useful here, I will just highlight, is that lipids survive particularly well in more acidic conditions, which are conditions that tend to be much less good for other kinds of datable organic materials like bone. So I will finish here before I'm thrown off Zoom. Very happy to talk more or take any questions. What I would direct you to, if you're thinking about a project, is our guidance, which has been published through Historic England, that's freely downloadable from the Historic England website. Gives you lots of information about the approach, sampling strategies, and so on. And also, if you have any questions, do get in touch with us at this email address here, which has got a team of people, including myself, who can get back to you with your specific inquiries. But thanks very much for your attention.
Thank you, Lucy. We do have a question in the chat that we've got time for. Richard Brunning asks, or sort of says, sometimes new pots are boiled in milk for proofing, so dairy lipids could be introduced from proofing rather than use. Presumably, if that happened in the past, it would give a false impression that the vessel was used to hold milk products. Have you got anything like to add to that?
Yeah, no, it's a really good point, and yeah, something we thought about. We've done some experiments to look at. It's amazing actually because we've done this sort of waterproofing by boiling milk in or putting milk into hot pots, and you get this kind of milk volcano that comes out. But then you're left with this kind of varnish on the inside of the pots. It's quite amazing. What I would say is, yes, that could be possible. But you get overprinting. So if a pot was used, if it was waterproof with milk, but then it was used over its lifetime for predominantly animal products, you're going to start overprinting that milk signature, and it's been shown experimentally, you're going to start sort of increasing the pots used each time. You'll replace that with the animal meat instead. So it would start to be sort of, unless it's only being used for, say, water after that, you're probably not going to see that. And one single use would probably also result in fairly low lipid recovery. But yes, it is entirely possible.
One more question from Catherine Bradshaw. As you said that the presence of lipids isn't seen visually, are there ways of knowing which sherds might give the best results for analysis?
Oh, we'd like to do lots more work into that. I mean, generally, from my anecdotal experience, it depends on things like burial environment. So more acidic conditions are quite good. Calcareous tend to be less good. Climate, Britain is pretty good. If it's very arid, it tends to be good. If it's sort of cold and dry, that's good. Mediterranean's a bit rubbish because it's sort of warm and wet. Then in terms of the pot fabric itself, the harder fired sort of Samian ware is rubbish. But if it's fired at high temperatures where you sort of get this almost semi-vitrification, that's pretty poor. The really nice stuff is your nice kind of Neolithic, sort of fairly coarse stuff where the lipids can absorb into it. So the fabric does have an impact as well. And then the last couple of things are how it's used, which of course you don't know because that's you're finding that out. But if it's used for lipid poor stuff, it's like mortaria, they're going to be pretty rubbish. And what's my last point? Oh yeah, the location of the sample as well will have an effect. So pots that are used for boiling, the lipids tend to accumulate towards the rim of the vessel. So if you're going to take a sample from what you think is probably a cooking pot, sampling around that rim where the lipids kind of both wick up the side of the pot but also float on the top of the water, that's where you're going to find your highest lipid concentrations.